Now we'll formally move into section 13.2, which is tests concerning means. And all the tests in this section assume that the random samples are either drawn from normal populations or that our random samples are large enough to justify using normal approximations. Obviously, the two examples, or the one example that we just looked at from two different perspectives, falls under this category because we had a large enough sample that we could justify using a normal approximation. So when we're working with one sample tests for a population mean, it will involve testing the following hypotheses. Typically, our null hypothesis will always state that the mean is equal to some value mu naught, which is some real number, and that'll be juxtaposed against an alternative hypothesis that's one of the following three options. Either that mu is not equal to mu naught, in which case we refer to that as a two-tailed test, or that mu is strictly less than mu naught, in which case we call that a left-tailed test, or that mu is greater than mu naught, and we'll call that a right-tailed test. So we're going to start much like we did with confidence intervals, and everything we do in this section will parallel what we did in Chapter 11 with respect to constructing confidence intervals for a population mean. In particular, let's talk about the Ztest procedure for one sample mean. We'll start with assumptions that we have a random sample of size n drawn from a normal population with known variance. And from Chapter 8, Theorem 8.4, we know that then the distribution of x bar is normal. So that means that when we go to compute our test statistic, we're just going to standardize x bar by computing the z-score, x bar minus mu over the standard deviation divided by the square root of n. However, what if the original distribution is not known to be normal? Perhaps we don't know anything about the shape of the original distribution. In that case, if our sample size is greater than or equal to 30, and if sigma squared is known, then our central limit theorem applies, so the distribution of x bar is approximately normal regardless of the original distribution. We'll call this our large sample z-test. However, it's also worth noting that if sigma squared is not known, much like we did with confidence intervals, we can just use the sample variance s squared to estimate the population variance of sigma squared. As a consequence, our test statistic will still be a z-score, but we're computing it by doing x bar minus mu over the standard deviation from the sample divided by the square root of n. Next, we consider the critical regions for the z procedures. And our rejection regions are going to be constructed based upon whether or not we're working with a left-tailed, a right-tailed, or a two-tailed test. In the case where we're working with a left-tailed test, and our alternative states that mu is less than mu naught, what we'll do then is we will chop off an area in the left tail under our z distribution such that the area in the tail is equal to alpha, our risk level. Then that tells us that our rejection region will be the set of z values that are less than or equal to the negative z alpha score. Similarly, when working with a right-tailed test, if our alternative hypothesis states mu is greater than some number, mu naught, then we will chop off an area in the right tail under the z distribution such that the area is equal to our risk level alpha, and our rejection region then becomes the set of z-scores where z is greater than or equal to z alpha. Finally, for the two-tailed scenario where our alternative hypothesis states that the mean is not equal to mu naught, then we're going to take that risk level of alpha, divide it in 2 to get alpha over 2, and chop off area in two tails, the left and the right, where each tail has an area of alpha over 2, so that our rejection region then will be the set of z-scores such that z in its absolute value is greater than or equal to the z alpha over 2. And this is the scenario that we just used in our previous example. Our next question is, how will we deal with small samples? So as with confidence intervals, if our sample size is less than 30, but our random sample is drawn from a normal population and the variance is unknown, then we will use the t-distribution, and our test statistic will be a t-score, where we will make use of the sample standard deviation instead of the population standard deviation, and our rejection region will be constructed using a t-curve and the appropriate number of degrees of freedom. So remember, our number of degrees of freedom is equal to n minus 1 when our sample size is equal to n when we're working with a t-score for this random variable. And our rejection regions for the left-tailed test will be the set of values for t where t is less than the negative t alpha score with n minus 1 degrees of freedom. Likewise, for the right-tailed test, the rejection will be the set of t values where t is greater than t alpha with n minus 1 degrees of freedom. And the two-tailed test will have a rejection region that's the set of t values such that the absolute value of t is greater than t alpha over 2 with n minus 1 degrees of freedom. So again, we're taking that significance level of alpha, chopping it up into two equal regions, alpha over 2, dividing it into the left and the right tails. And actually, I just realized that I've got a couple mistakes above. We really need to be careful. These rejection regions should all have inequalities, not just strictly less than or strictly greater than. They should either be less than or equal to or greater than or equal to, so I've adjusted them here. So let's consider an example where a chemical process has produced on average 800 tons of chemical per day. The daily yields for the past week are 785, 805, 790, 793, and 802 tons. Do these data indicate that the average yield is less than 800 tons and hence so that something is wrong with the process? Let's perform a test at the 5% significance level, and along the way we're going to need to determine what assumptions are necessary for this procedure to be considered. So notice that our sample size is 5, which is strictly less than 30, and our variance is unknown. As such, we're going to have to make an assumption that this random sample is drawn from a normal population so that we can perform a t-test. If we couldn't make this assumption, or if it was truly wrong to make this assumption, then our only other avenue would be to do something called a non-parametric test, but those types of procedures aren't discussed at all in this course. So for the moment, we're just going to go on this assumption that we're drawing from a normal population so that we can perform a one-sample t-test. Let's define our hypotheses and specify our alpha. We know that we're testing at the 5% significance level, so that tells us that alpha is equal to 0.05. And for our hypotheses, we'll let the null hypothesis be the statement that mu is equal to 800 versus the alternative that mu is strictly less than 800. And now when we look at this alternative hypothesis, we see that we're stating that our mean is less than a specific value, so that's going to tell us that we're going to perform a left-tailed test. Now let's determine our rejection region. So we start off with alpha equal to 0.05. We know our number of degrees of freedom is 1 less than the sample size, so our degrees of freedom is 4. So since we know we're performing a left-tailed test, then the first thing we need to do is find a critical value for the t-distribution where the area in the tail is 0.05 for 4 degrees of freedom. If we look up into the t-table, we'll see that t.05 with 4 degrees of freedom is 2.132. So the rejection region for this left-tailed test is the set of t-values where t is less than or equal to negative 2.132. To compute our test statistic, the first thing that we have to notice is that we were just given data. As such, we need to find the sample mean and we need to find the sample standard deviation. Using a calculator, we get that x bar is 795 and s is 8.34. So then we're going to compute our t-score, so we'll take our mean of 795, we'll subtract the mu, which is given to us by our assumption in the null hypothesis that mu is equal to 800, then we'll divide by our standard deviation of 8.34 over square root of the sample size, which is 5. And we'll get a t-score of negative 1.3. So for our decision, our test statistic of negative 1.34 does not lie in the rejection region because negative 1.34 is actually greater than negative 2.132. So that tells us that we're going to fail to reject the null hypothesis. So our conclusion here is that there's insufficient evidence to suggest that the mean amount of chemical produced is less than 800 tons per day.